Hi and welcome back once again to this series of video, and if you recall, we were discussing a story about my rocket, my favorite rocket, which is here, and we were discussing the physics of this rocket, how it works. So we said that this rocket is fitted with a jet engine behind it, and it throws out a mass of gas when it is ignited, and that gas comes out at high pressure from the nozzle behind it, which generates a backward momentum, and due to the Newton's third law of motion, the total momentum of the system must be conserved. Therefore, the rocket attains a forward momentum which is equal to the backward momentum of this rocket. Okay, so when this rocket is ignited, so if this rocket is ignited, then gas comes out at once. Okay, so everything happens at once. It takes no time for this amount of gas, this mass of gas to come out. Okay, so it happens in a very tiny fraction of time, tiny fraction of second maybe. Okay, and therefore the rocket moves forward, and we said that if the velocity of this gas coming out from the nozzle is u and the mass of this gas is m, then the momentum, backward momentum, is mu. If the mass of the rocket is m, then the velocity that it should attain in the forward direction, if that is v, then Newton's third law, or conservation of momentum, implies that mv is equal to mu, or v equals mu by m, and this velocity is attained at once. It takes no time for the rocket to attain this velocity from zero velocity. So if I draw the time axis, if the jet is ignited at this instant, okay, at this instant of time, then the velocity before this was 0, the rocket had no velocity, and at this instant the velocity goes instantaneously to this value of v, right? It takes no time, or almost no time. And after this, the velocity decays exponentially. We said it decays exponentially because of air friction, which tries to oppose the motion of any object moving through the air, and therefore the velocity decreases. And this is how the velocity pattern, or the velocity as a function of time, looks like. It drops slowly, asymptotically, to 0. Okay, and this pattern, let us derive mathematically how should this pattern look like. So let us do the derivation of v as a function of t. If we call this as t equal to 0, then how does the velocity change as a function of time? Recall that we assumed that the air friction, or force opposing the motion of the rocket, is proportional to the velocity mu times v t, where mu is the coefficient of proportionality, or you can call it the coefficient of friction coefficient, and this is the force opposing the motion, and therefore m times v m times v dot t, which is the acceleration, should be equal to this force, and this should be equal to mu times vt. Okay, I should have a minus sign here to indicate that the force is in the direction opposite to the velocity. So mass times the acceleration of the rocket is equal to minus mu times vt, right? Now we have v dot by v dot t by vt is equals minus mu by m, right? So I bring v from here to the left side and I take m to the right hand side, so I get this. Now I can integrate it over time, integrated over time dt, this also integrated over time dt. What I will have is as follows. So this implies, okay, log of Vt is the integration of v dot by v, and if I do this integration from 0 to t, then I have it 0 and t. The right hand side, this is a constant, so this will be mu by m, sorry, there is a minus sign, times t integrated from 0 to t. Okay. Now this further implies that log v t minus log v 0, which is the initial velocity, is equal to, if I put these values, minus mu m by t, right? This implies log of vt is equal to log v0 initial velocity minus mu t by m, or I can write vt is exponential of log v0 minus mu t by m. This is equal to e to the power log v0 times e to the power minus mu t by m, and this is equal to v0 e to the power minus mu t by m. So therefore the velocity is decreasing exponentially as a function of time, with this mu by m being the time constant, or rather m by mu being the time constant, and this goes down exponentially from an initial velocity of v0. Now let us look at another function, which is which is the amount of gas burned as a function of time. So let me draw this. This is my time axis t, and up to t equal to 0 no gas was burned, and then at t equals 0, at this instant, m amount of, or a mass of m of gas is burned. So at this instant the amount of gas which is burned is m. Okay, and after this no gas is burnt again until the next excitation. So no gas is burnt up to this time, no gas is burnt after this point, but a total amount of m or total mass of m amount of gas is burnt at this instant, right? Okay, if we now call this y, so x-axis here is time. If we now call this y-axis as being the rate of burning or rate of fuel burning, okay, then the rate of fuel burning is 0 up to t equal to 0 and is again 0 after t equal to 0. But at this instant it should be very, very high, because we know that a finite amount of gas or fuel is burnt within almost no time or within almost 0 time. That means the rate of burning is very high, tending to infinity. So this goes to infinity, but the total amount of gas or total amount of fuel which is burnt is a finite amount, that is equal to m. So the total amount is finite, but the rate of burning is infinite. Now we know that if we integrate say this is the curve, if this is the curve of rate of fuel burning, then if we integrate the area under this curve, that gives me the amount of fuel burning within a time. So if I integrate the rate of burning from here to here, then the result of integration, which is equal to the area under this curve, is the amount of fuel burnt within these two times. Now in this case we know that the total amount of fuel which is burnt is m, therefore the integration or the area under this curve should which is equal to the total amount of fuel burned between these two times should be equal to m. However, this height or the rate of fuel burning at this point should go to infinity. Such a function is called a impulse function. So this rate of fuel burning is an impulse function, because the fuel is burnt impulsively in no time. So there was no fuel burning up to this, and then boom, everything burned at once, and then again it stops. However, the area under the curve is finite. I mean, this is sometimes quite counterintuitive. How is it possible that this spike is so narrow, yet it has a finite amount of area under it, and again it has an infinite height? Sometimes it's difficult to visualize, but try to realize the fact that the height of this curve is infinite, almost infinite, whereas the width is almost 0 and the product is finite, which is equal to m. And this is an impulse function. Such a function is called an impulse function. Now what we have seen, that when the gas is burnt like this, so this is how the gas is burnt, like an impulse function. This is how the velocity changes, the velocity of the rocket changes. So this is t equal to 0. So this curve we can call it as excitation, or is the cause for the velocity, and this is the response. So this is the excitation caused to the rocket, and this is the response of the rocket. So excitation here is an impulse function, and the response is an exponentially decaying function. this particular response, which is against this particular type of excitation, has a specific name. This is called an impulse response or impulse response function, because this is the response to an impulsive excitation, right? That's why we call this is an impulse response or response to an impulse function. We can also call this as an unit impulse response if this is a unit impulse function. What is an unit impulse function? So an unit impulse function is one where the area under the curve is equal to 1. In this case, the area is equal to m. Now if m equal to 1, that is if 1 unit of gas or fuel is burnt, then we will call this as an unit impulse function or unit impulse excitation, and then we can call it as an unit impulse response. Sometimes the term unit is not mentioned and we only call this is an impulse response, and the word unit is implied, it's taken for granted. If you just say impulse response, it often means it's unit impulse response or the response to an unit impulse function. Okay, so now let's move on. Let me bring back my rocket once again and let me reiterate the fact that this rocket burns fuel impulsively. So suddenly fuel is burnt, boom, and it moves, stop. Again, boom, moves and stop. And then we saw how to find the velocity of this rocket as a function of time. So what we have to do, we have to first draw a time axis, identify the points, say t equal to 0, then t equals say 1, t equals maybe 1.5, 2, etc., where the rocket, the engine is ignited or excited, and then we need to know the amount of gas burnt in those instances. If the amount of gas burnt at t equal to 0 is m, then we know that the velocity thus attained by the rocket will have a profile like this, where this starting value is equal to v given by mu by capital M. Now if again another burst is created at this instant, and if say the amount of gas burnt here is say 0.5 m, so this is this will be 0.5 v, sorry, 0.5 v. Okay, so this was v, here only half of m amount of fuel is burnt, so the velocity profile will be half v, starting from half v, exponentially decaying to 0. And then we have to draw all such impulse responses at starting from all the instances where the gas is burnt, each having different heights corresponding to the amount of gas or fuel being burnt there. And then we have to sum up all these curves. So the summation then looks like from here it goes up, from then here, then again it goes up further and then goes down. Here I have to sum up all three values going up to this point, then it goes down. Here again goes up and goes down. So this is the sum of all these individual impulse responses. once again we can follow this graphical technique, this graphical method is which will give it a name soon, or let me give the name now, is called a convolution. Okay, this method of convolution is applicable or valid only if the rocket satisfies certain properties. Which are they? Number one, the rocket should be linear, which means it should be homogeneous and it should obey superposition. By homogeneity, we mean that if double amount of gas is burnt, then the velocity profile for the velocity value at any instance is doubled. If 10 times gas or fuel is burned, the velocity curve becomes 10 times at each instance of time. So that is homogeneity. By superposition, what we mean is that if there are two bursts like this, one here, another here, then the resultant velocity at any instant is the sum of the individual velocities. I mean, of course we that need it, because that's how we calculated the final velocity, by adding individual velocity curves. So we have to, I mean, that should be a valid, I mean, that should, for that to be valid, we need this superposition principle to be obeyed by my rocket. Then we also need it to be time invariant. Time invariance. By this, what I mean is that if the impulse response at t equal to 0 is like this, then the impulse response at t equal to 10, 100, 1000 or anything should be again like this. We also say that it won't be time invariant if, for example, say the rocket is losing some mass because it is burning fuel, and therefore its mass capital M is reducing, and therefore now at t equal to 100 or 1000, for same amount of gas or fuel being burned, it will attain a higher velocity because now the rocket is lighter. In that case, it won't be time invariant. Therefore, we assume that the rocket is much heavier than the total amount of fuel it is carrying. Therefore, the effective mass of rocket remains same. So that is what time invariance is. So let me quickly summarize what we have discussed so far. We have discussed what is an excitation function, what is an impulse function, what do we mean by impulse response, simply the response to the impulse. We have discussed the graphical method of convolution to obtain the velocity by adding the response to individual impulses or individual rocket bursts, and we have discussed the properties that must be satisfied by the rocket so that we can apply this method of convolution, namely the time invariance and linearity properties. Now, after all this theory, I realized that my rocket is not comfortable for me. So this rocket is not. So this rocket is not comfortable. Why? Simply because it jerks quite a lot. I mean, I have to ignite the engine, it moves suddenly, boom, and then it stops. Again I have to ignite, then it moves suddenly and stops. So it's very jerky, its motion is very jerky, goes and stops, goes and stops, goes and stops, and when I ride this rocket, I feel quite uncomfortable in this rocket. So I decided to change the engine and upgrade my engine to a newer version, and here I have version 3 of my engine, which is here. So this is version 3 of my engine, and this one burns the fuel slowly and smoothly. So this new one burns, so the new engine burns fuel slowly and smoothly. Okay. Therefore, if I draw the fuel consumption or rate of fuel burning as a function of time, so this is time and this is rate of fuel burning, then previously it was impulsive. Okay, so previously it was like this, suddenly m amount of gas, again suddenly 1.5 m amount of gas, again suddenly 0.5 m amount of gas. So this was how the fuel was burning in my previous engine, and the new engine is much better than this. So this burns fuel slowly and smoothly like this. Okay, so this is no longer an impulsive curve but a smooth curve. But now I am in another trouble. The trouble is that I have to compute the velocity or estimate the velocity at any instance of time, and I cannot apply the previous trick of summing of these impulse responses at the time of occurrences of engine ignition. Here the engine is always on, it's slowly and smoothly burning the fuel. So how do I find the velocity at any instant? So it's going to be a bit difficult, but not that difficult. We can still solve this problem, and here is how we do it. Let me redraw this curve once again. Okay, so this is how the fuel is burning as a function of time. I will decompose this into small patterns like this. This is one, then this is two, the green one, then this is three, the yellow one. Let me set it with color. Okay, yellow, green, and before that I had blue, and so on. Here I can have a orange one, so on. So what I'm saying is that this function can be decomposed into this several functions like this. So here this orange one, next one here, this blue one, right? And okay, okay, so this is the overall profile. here again this is the overall profile of gas burning, and I decompose this single function into a set of functions like this. So 1, 2, 3, 4, here 1, 2, then I have also 3, 4, etc. and I have so many of them, right? Now let's look at one of them. Maybe let's look at this one, the blue one. Let me call this time where this blue curve starts as, say, let me call it T1, this instance where this blue curve starts, and T2, this instance where this blue curve stops. And let the height of this curve here be something like x T1. Okay, if I assume that it's almost constant, if I take the width of this blue curve to be very small, then this height I can consider to be almost constant, which is equal to xt1 or equal to xt2 if it is very small. Then the total amount of gas which is burned within this period is equal to, so here m within this blue curve is equal to xt1, this height, times this duration, which I call as T2 minus T1, right? Now if this width is very small, right, then I can assume that this is a impulse function, or it's tending to an impulse function, in the sense that the duration or the span where this function is non-zero is tending to 0, and the area under this curve is equal to this. So this I can assume to be the value of this impulse function, right? So xt1 times t2 minus t1 is the value of this impulse function. Therefore, I can assume that this blue patch or blue bar is equivalent to an impulse function, and the response to this function, if I draw it here, okay, so this is t1, so the response to this function will be again exponential, and what will be the height here? This height will be proportional to the area under this curve, that means proportional to the total amount of gas being burned, because we know that here V, this height V is equal to mu by m, and where this m is equal to x t1, where x is this curve as a function of t, so this is xt, okay, this is xt, so xt1 times, and if I call t2, if t2 is equal to t1 plus some delta t or dt, then t2 minus t1 is dt, so xt1 times dt is equal to m. So this is m, this multiplied by u divided by m. Now u by m is a constant for my rocket, where u is the velocity of the gas being thrown out, and m, which is a constant, and the mass of the rocket, which is again a constant. So this is a constant, and therefore we see that the velocities, the starting velocity is proportional to this area under this curve, xt1 times dt. Right? Now what we can do is as follows. Let's move on to a fresh page. Okay, so here I have time axis. This is the rate of fuel burning. I'm just repeating what I just said in the previous slide, previous paper. Okay, and this is chopped into narrow slices like this. Okay, and the width of each slice is dt. Okay, and then here I'll find the velocity of the rocket. So velocity, I'll find it graphically as a function of time. Okay, and to do that, let me draw two more functions. So we know, we have seen that if here m amount of gas is burnt instantaneous, I mean in no time, within, so if it is an impulse excitation, m amount of gas is burnt almost in no time at this instant, then the rocket's response velocity becomes like this, exponentially decaying, starting from a value of v, where v is equal to m u by m. Now let me call this u by m a constant k. Then it is like m times k. Therefore, if m is equal to 1, if one amount of gas or unity amount of gas is burned, then the starting velocity is equal to k and decreasing exponentially. Right? Now here, let's come back to this curve. Here we see that at this time, a total of, okay, if I call this as xt, this curve is xt, which is the rate of fuel burning or the amount of fuel burned per unit time per second. Then if this point is t1, then this height is, or in general if this is t, then this height is xt. Now this height xt times dt is the area under this curve. Now this is when the dt is very small, I can think it as like a impulse function. Therefore the response to this excitation will be, let me draw it with blue color. Okay, so this is the response of velocity response of the rocket for this this amount of gas or fuel being burned, and this height will be equal to, so this height will be equal to k times xt dt, right, where k is this. Then for this orange one, I have to draw another exponential function. Then for this green one, I have to draw another exponential function, and so on. I have to go on, and then I have to add up all these functions to get the velocity of the rocket at any instance. Right? Okay. Okay. Now this is how we can do it graphically. Now let's do it algebraically, mathematically. Okay. So once again, let's look at this impulse response function. So this is how the velocity varies as a function of time when an unit amount of gas is burned. So okay, what is the expression for this curve? So the starting value is k, and then it goes down exponentially. So here, if this is t equal to 0, right, then here at t equal to 0 the value is k. So Vt is equal to k, and then e to the power, it's decreasing exponentially, minus t by tau, where tau we can estimate from here. Tau is m by mu. Tau is m by mu, and k here is actually v0, the initial velocity, right? So this is the impulse response function, and as it is common in electrical engineering or in control system, we always use the symbol h or ht to denote impulse response. So the symbol h, I don't know why h, but it is common, it is universally accepted that h stands for unit impulse response. So now let me use the symbol h instead of v. So I strike out v, which stands for velocity, but since it's the response function for unit impulse, I'll use the symbol h. Okay, this is just a convention. Here h is same as velocity. Okay, so now this is given, ht is given, and from this ht I have to find out the velocity at any instance by adding up these individual curves. I'll now also use the symbol yt for the velocity of, the final velocity after adding these individual individual components. So when I add them, so this is the final velocity. So I'll use the symbol yt, which is customary, which is standard in electrical engineering and control system, to denote the output or response of anything. Here in this case it's again velocity, and xt is used for x for input, y for output, h for impulse response. So xt here I'm using for the rate of fuel burning. I'll use the symbol yt for the velocity, final velocity of the rocket after adding these individual curves, different color curves. So that's yt, and ht is the impulse response. Okay. Another symbol that I'll use is delta t. So delta t stands for unit impulse. So if the area under an impulse function is 1, then that is represented with the symbol delta, and if this function is active at t equal to 0, then we call it delta t. So delta t means is a unit impulse which is 0 anywhere else other than when this argument inside bracket t is equal to 0. So that is delta t, right? So now we know from the physics of the rocket that we have discussed so far that if a unit impulse excitation is given at t equal to 0, that means if at t equal to 0 one amount of or 1 kg of gas or fuel is burned, then the response function is this, k e to the power t, or in general ht, right? So if the excitation is delta t, that means, okay, let me draw the corresponding functions also. And here I have the response. Okay, Okay, when delta t is the excitation, so that means at t equal to 0, one amount of gas is burned. The response is ht, which is like this. This is t equal to 0 and then an exponential function. So that means if if I now delay this function or delay this excitation by an amount tau, so by this I mean that instead of burning the fuel at t equal to 0, I wait until t equals tau. So this is the point. So this is the point tau. So I wait until t equals tau and then I burn 1 kg of fuel here. Then the response will also be delayed. So it won't start from here, it won't start from 0. So this is 0. Instead it will start from the point tau, and here how the velocity should look like. So this function I should then call ht minus tau. Why? Because if I write t minus tau, then when t is equal to tau, when t is equal to tau, then this is 0. So it takes the value of ht for t equal to 0, that means it takes this value, right? So when t is equal to tau, it takes this value. So this point comes here. Similarly, all the points are shifted by tau amount. This point comes here, this point comes here, this point comes here, and so on. So this is ht minus tau. Now, okay, next, let me write it here. If I now multiply this delta t minus tau with some value x tau, okay, x tau delta t minus tau, right? So then what happens? This function is scaled up, it's enlarged by a factor of x tau, right? So this is tau, this point is 0, okay, so this is 0, this is tau, right? And then the excitation should also get scaled up. So this is 0, this is tau. So here I should have a larger exponential like this. So this function then should be x tau h t minus tau. So previous one multiplied by x tau, right? Okay, now now let us look back again at this curve. Okay, so here, okay, in this curve, instead of using this symbol t, let me use symbol. So to denote this point, let me denote this point by the symbol tau. Okay, so this point is tau, so that means this is x tau. Okay, and let me call this width as delta tau. Okay, not dt but d tau, right? So that means let me come here. So this is my table, excitation versus response. Okay, so here I see that if I have an excitation of x tau times delta tau. So this is the, because this is the area under the curve, so this is equivalent to an impulse function with value x tau delta tau, right? So if I have excitation which is an impulse function at t equals tau, at t equals tau, it's an impulse function with the value x tau d tau, right? Then, so this looks like this. At tau, this is non-zero and the value is x tau d tau, right? The response should be again then like this. At tau it starts and the height should be scaled by x tau d tau. So x tau d tau times h t minus tau, delayed ht, right? Okay. Now what I have to do next is I have to add up the response function, all this response for different tau. So this is the response for this blue patch, right? So this is the response for this blue patch, this curve. This blue curve is the response for this blue patch, which is here. I hope it's visible. So which is this one. Okay, so when I have this blue excitation which is equal to x tau d tau, right, the output is x tau d tau times ht minus tau is here. Now similarly, when I have this orange one, let me write it here. So the orange one will have a height of x tau plus delta tau, right? It has a height of tau plus x tau plus delta tau, area delta tau, d tau multiplied by the impulse function delta t minus tau and minus delta tau, right? Because it is delayed further. So it starts not from here but from here. It's here. Okay, this is delta tau, right? Then the output will be x tau plus delta tau times this delta tau into h t minus tau minus delta tau, right, and so on. Now I have to add up all these functions for tau equals minus infinity to plus infinity to get the final response. So adding in this case is equivalent to doing an integration if this d tau is very small, if this width of these individual patches are very small, then adding all these individual functions is equivalent to adding or taking an integration over tau equals minus infinity to plus infinity, right? Let me now rewrite the same thing a bit more clearly because I was running out of space. I'm sorry for that. So let me copy this here. So again, this is the input or excitation input, on the right hand side is output. So we have seen that x tau, I'm just copying this line, x tau delta t minus tau d tau. I'm just reorganized, I have reorganized by taking d tau at the end. So this quantity integrated over t equal to minus infinity to infinity, the output, corresponding output should be this quantity integrated over t tau minus infinity to infinity. So this quantity I'm just copying again, x tau ht minus tau x tau h t minus tau, then d tau I'm taking at the end, integrated over tau equals minus infinity to infinity, right? So this is the input and this is the corresponding output. Okay, now definitely this is the input, this is the input as a function of time. Okay, so this integration is carried over the argument tau. So after this integration is carried over, tau, the variable tau will be eliminated from the expression, t will remain. So this will be a function of t. Similarly, the right hand side or output will also be a function of t and not of tau after the integration is carried over, because then tau will be eliminated. So this is again a function of t, this is also a function of t. So this is the input as a function of t, and without even doing much mathematics you can readily state that this is equal to xt, because nothing else, because this is my input and we know that this is xt, and this xt is being chopped into small pieces like this. So this blue piece is one chop which is an impulse function at t equals tau. So this blue piece is delta t minus tau with an height, with a value of x tau d tau, right? So this is the equation of this blue patch. Similarly, we can have the equation for this orange, green and all other patches, and then they are added up. So they are added up here, they are integrated. So they are integrated here. So this definitely, we know when we add all these patches, blue, green, orange, everything, then this becomes equal to xt. So this is xt. And this is the output that we wanted to compute. So by the definition, because we denote output as yt, so this is yt, right? So then yt is going to be this. And so this is how the output or the final velocity of my rocket is going to be. Yt is x tau ht minus tau d tau integrated over tau equals minus infinity to plus infinity. And this is symbolically, notationally denoted as like this, a star in a circle, ht. Okay, so given xt, which is the input function, excitation function and the impulse response function, using these two we can derive the output by this formula. And this formula in shorthand, in shortcut, is written like this: x tau h tau. This is called a convolution. Convolution. So this symbol, the star within the circle, stands for this operation of convolution. So given xt and ht, we add them in this manner and we get the output. Okay, so this is how we can get the velocity when the excitation or the rate of fuel burning is not impulsive, not like boom, 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 but it's smooth, like something like that. And then my journey is comfortable and I'm happier with this newer version of my engine 3. Thanks. Let's meet for further discussion in the next video. Thanks.